Hi, everyone. My name is Hugh McKee. I'm a developer advocate at Lightbend. And this talk I'm going to be going over, as you can see, is a lot about serverless code, data, and in Java. So the want to do a few visuals, I guess, call it a few slides. And the first thing I want to get to is just stateless and stateful. I just want to show you a little bit about the differences between stateless and stateful, because what I'm going to be showing you is a serverless offering is something that's stateful. So often when you hear about serverless, we hear, oh, of course, there's servers. It's like, yeah, okay, we understand that, right? But the other thing though is with stateless, there is state, and that's what our systems do. So really, one way to think of our applications is that they're state management systems. So when you implement a microservice, or you implement a monolith, or some kind of whatever it is, a function as a service, whatever. Often those things are in some way or form manipulating state. So, what's the difference between stateless and stateful? Well, I'm going to try and show you that with just a few visualizations here. So, and hopefully this comes through on the video. But the idea is that with stateless is a very, very common pattern. We've been doing stateless for a long time. Stateless monoliths, microservices are often stateless, and it's a very mature way of doing things. There's great technologies for doing it. And one of the main motivations for doing stateless is that the computations are mobile. And what I mean by that is, as requests are being processed by the system, those requests can come into any server. So say this server here, I'm going to kind of simulate a little spike in traffic where say we get a spike in traffic on this node, say your app gets a spike in traffic, and this one app server that's handling all this traffic is getting overloaded. What is easy to do with a stateless system by design is that you can simply add more app servers, or more backend processing. So more instances of things, so you can scale horizontally. So the compute side can scale very nicely, and again, this is I think one of the core features of a stateless system. Now, the process that occurs is kind of interesting, and I've got a kind of an animation here for that as well. So I'm going to just play this, and it'll keep running as we go. So a request comes in that triggers the recovery of state from the database, and I call it kind of the database cold state. And then the state's in memory, and we can process that. So again, it'll repeat here. A request comes in, we recover the state from database. Now it's hot in memory. We process it, and we write the state back, and we send back a response. So the cycle repeats over and over again. And on each cycle, we recover that state. We bring the state into hot state, where on the compute side. But then when we're done with that process, with that, processing that request, we throw the state away. And this gives us the mobility so that every single request coming in to perform some operation can land on any, instance of the backend application, however it's distributed, scaled horizontally. Now, the approach with a stateful system is very similar, but with a bit of a difference. So I'm going to run a stateful processing flow, and it's very similar. A request comes in. Initially, there's no state, so we have to recover the state from the database. So now we have the state in memory, and we process it. We write back the state changes back to the database, send back a response, but the change that happens here, the state stays hot. So the next request comes in. We don't have to hit the database again to get the state. We make the change, we write it back, whatever changes to the database. And the savings here is that we're not, having to do that read of recovery of the state every time. Now, conceptually, this is very easy to see. I mean, we're just watching this process. The actual implementation is not trivial. And so that's one of the reasons why we went with stateless for so long, is that it's a much simpler, there's less moving parts and those types of things. But when you can solve this problem, we get this big savings here of not having to constantly recover the state from the database. So this is kind of the flow that's going on. And the idea is that we're changing things in some really interesting ways. Of course, the first savings is that we're reducing the IO load on the database. And in my experience, and I've been building backend apps for a long, long time, even before we were called, before stateless was a thing, I was building stateless systems. I've been doing this for a long time. Often the point of performance problems was the database, that because we delegated so much of the work to the database with locking and contention management and state management, all that is being handled by the database. Anything that we could do to reduce the load on the database was a good thing. So having a stateful system where we're at least eliminating some of the reads, not all the reads, because we have to recover the state, initially if it's not in memory somewhere. But when you can do this, it's a nice optimization. But there's a really interesting thing that occurs now. Instead of, you have this single writer, and what I mean by this is that there's almost this inversion of state, where the master of the state isn't in the database necessarily, it's in the system. That the single point, when you have a single writer where there's only one instance of a state of, say, of a shopping cart or an IoT device or a customer record or inventory information, whatever it might be, there's only one instance of that state anywhere in a distributed system. When you can solve that problem, you get this inversion of state, and the master of the state is in the computational space, not in the database space. It's also a form of concurrency isolation, because there's only a single writer. Locking is kind of a natural thing where you're not having to depend on database locking necessarily, because there's only one place that can handle a state change. And by design, the state change operations handle one request at a time. But it's by, it's a very fine-grained form of concurrency isolation, where it's just, every shopping cart has its own instance that's being changed. So it's quite interesting what occurs when we go into this. So enough slides. I want to show you a implementation of this in action with something that my company has been working on called Akka Serverless. And with Akka Serverless, it's an implementation of writing stateful functions as a service, basically, but of very specific types, and I'll show you that. But just to kind of dive into the code, if you take a look at Akka Serverless, and it's in beta right now, and it's going to be generally available next month, is the plan. So you can give it a try, you can check it out, it's free. There's free trial periods, and right now it's a free beta. But in any case, one thing you'll see is that we say it's API driven. What we mean by that is that in the way you set up a particular piece of functionality, it's done using what are called Google protobufs. And these Google protobufs is, it's a kind of a syntax for defining things like APIs. And it's pretty straightforward. I had never seen Google protobufs before I started looking at Akka Serverless not too long ago, because this is all brand new. But it's pretty straightforward. You define messages. So you can see, like, I want to implement a shopping cart service. And to do that, I define the API of the shopping cart service. So I've got a add line item, change line item, and you can see that there's certain fields in it. So there's a certain syntax for defining these messages for my API. Pretty straightforward though. You can, I define a line item. I define my cart, which is composed of some data and the line item. So this is my state object right here, this cart. So I define that in this API. But the other thing you do is you define the service definition. And here is where I say, all right, I want to implement this function as a service, basically as a cart service. And this, again, this is all protobuf syntax, but you can see there's these RPC definitions. So there's add item. It takes in a message that is a add line item that I defined earlier, and it returns an empty, just kind of an acknowledgement. Yep, I added that line item. Same thing for change line item, and so on. And then there's, finally there's like a get shopping cart that returns the shopping cart. Also note that this we generate where this will work with gRPC, but you can also define it to be HTTP, so it can handle RESTful HTTP types of requests as well using this. They call it an annotation. But basically, what you do is you create this file, you define your API. There's another protobuf definition that describes kind of the service on the inside. So the API describes the service on the outside. What does the service look like to the outside world? This other one is often called a domain definition that describes the domain, the data that it looks like on the inside. And the reason for doing this is to allow, say, the definition of the outside evolve at a different pace of the service as a definition on the inside. But pretty straightforward. Then what happens is that, in this case, this is, I'm doing Java. So there's a way to quickly set up a Maven. There's an archetype to create a Java template project. And that template project comes with a POM that's already pre-populated with a bunch of plugins. So when you do a Maven compile, it looks at these protofiles and it generates some code. And the code that gets generated, there's a bunch of code that gets generated in Target, but there's also code that's generated in source main Java. So you can see this class here that I've just pulled up. At the very top, this code was generated by serverless tooling. As long as the file exists, it will no longer be regenerated. So the idea is that it'll initially stub out this file for you, but then we go in as developers and we add our business logic to this file. So you can see that this class is it's extending an abstract base class. So this abstract class, the source code's in Target, and it's generated every time we do a compile. Whereas this source file is only generated once and won't get regenerated unless the file is deleted. So the idea is that if I change the protobuf definition, say I add another command, another API message that this guy should handle, if I don't, when I recompile, I'll get an error because I haven't implemented, say, one of the abstract methods. It's that kind of an approach. So in the actual code itself, I got this template. There was originally some just default returns. This add item hasn't been implemented yet. I replaced that and I just wrote my own code. So, and here's an example. I'm handling an incoming command. Now, one thing I want to say is that this is it. I don't have to worry about serialization. I don't have to worry about routing. I don't have to set anything up. If it's gRPC or REST, I don't care. None of that is my concern as a developer. All that's being taken care of by the system. All I do is write this code, and when a gRPC request comes in for an add item or a RESTful request comes in for an add item, then that request is going to be routed to my code here. So my code gets invoked, and that's all I have to worry about. So you can see that there's two parameters that are being passed to this method. One is the current state, this is stateful, and the command, so the add item command. So this reject or else handle, this is my personal style. This isn't something, say, that Akka Serverless dictates, but I just kind of liked this style and I kind of settled on it. So what I'm doing in reject is validation. Given the current state of my thing, in my shopping cart, and the command that I'm being asked to do, I'm going to just do some validation logic. And I'm returning an optional. So if something's wrong, I'm going to return an error response. If everything's okay, I'm going to return a empty response. So that's what the reject is. So if the command wasn't rejected, or else handle, so I just go in and do a handle. So in handle, the flow I use is I use the kind of a plain old Java object, the shopping cart class. So I'm kind of taking in the current state, and which is kind of a generated object, and I'm converting that into a plain old Java object, and then I invoke this handle command to handle the command, and then I convert the plain old Java object back to the stateful object, and then this update state. This method is where the actual write occurs. This is the persistence operation. So if you look at Akka Serverless, you'll see we call it database lists as well, because where this data is stored is being handled by the system. So there's no database connections, there's no users, URLs, passwords, schemas, all that stuff's gone. Don't have to worry about it, because so it's not the whole kind of object relational impedance mismatch type thing we hear about all the time. I'm just dealing with objects here. I'm just dealing with my state. I'm just dealing with the logic for handling the commands coming in, and that's it. So we're trying to what we're trying to do is with serverless, it's less. I like to call it dramaless, less drama, and frictionless, less friction, to get our jobs done. So really what you do is you focus on the business logic in the function. And this is it. So if we take a look at this handle method, I'm taking in the command. This handle method is in my plain old Java object class. I'm pulling out the cart ID, the customer ID. I'm pulling the new item out of the cart, and then I'm just returning this. So it's pretty straightforward, and I don't want to do that. So that's kind of the flow. Sorry for scrolling here. Yeah, and I just for all the commands, I ended up doing the same thing where it's add item, reject if it's not a valid command for the current state, if there's something wrong with the incoming command, or else handle it. And I just did it for change item, remove item, checkout, and so on. Pretty straightforward. Now, one of the things that I can do is, and I'm going to go fast for the sake of time here because I want to try and finish on schedule, is I can do a quick test. And I'm using Visual Studio. I really like Visual Studio. I've used IntelliJ for a long time, really like IntelliJ, but I wanted to try something different and love Visual Studio. And one of the things I like about Visual Studio is all the extensions. So there's this really cool extension called RESTful Client. And what I can do is I can take curl commands and put it into this source file in my project. And these curl commands I got from the Akka Serverless console, which if I had a little bit more time, I'd show you, but just trust me, I got these curl commands from the Akka Serverless console. In any case, what I can do is I can execute commands. So what I've done is to deploy this service, it's really the POM is set up. If you do a Maven deploy, it's going to deploy the service. Now there is some setup to do, not a lot. Mainly just saying, where is the image going to go? What Docker repo are you going to put it into? Are you going to put it in Docker IO? Are you going to put it in Google, Amazon, or whatever, Docker repo? But it's a Maven deploy. It deploys the service. That's it. It's done. And now I can test it out. So just real quick, I've already run some tests and I've added some data. And this is the response. I executed. Let me do that again. There we go. So I executed this command to retrieve orders by customer. So I've previously created a few orders for customer 1. And you can see cart 1 has a couple items in it, and cart 2 has a couple items in it. So what's really cool is, you can write unit tests. You can, of course, do that. You can also run this service locally. That's doable. But this is serverless. You can go fast. Write some code, deploy it to the serverless environment. The database gets set up. The code's running. Everything's good to go. It takes a few minutes to bring it up. That's it. Let's run a test. So that's what I was doing. So I set up all these different curl commands where I could add items, I could change items, I could remove items, whatever the API was that I built, and I just start doing some tests real quick here live, with the system itself. If I like it, if say you just want to try this out, you can deploy a service, you can play with it for a while, and then delete it, and it's all gone. No big deal. Super fast. So that's kind of the flow. The other thing I want to just briefly mention is that there's what I just did here was I queried the data from a view. So the data that's being stored by this service it's a key value as a service. So it's storing the data. It's storing the data in a state store. So every shopping cart has a state object that's getting stored in a key value store. In this key value state store, and the data is there, but it's not very queryable. So I wanted to have a query where I could retrieve all the orders for a given customer. So to do that, I created a view, and a view is also defined using this approach of using protobufs. So real quick, I just want to show you, define the view, and the main thing that's defined in this protobuf is the select statement. So I'm saying select orders from my state store where the customer ID is, the past customer ID. That's it. So the view is also set up databaselessly, not easy to say, without a database. No schemas, no nothing. I define this protobuf and do my compile, deploy the service, and all the data structures are set up for me. The code's ready to go, and I just, actually I didn't even have to write any code for this to work, because as changes occur to shopping carts, they're automatically being propagated into this view. So this is CQRS as a service, command query responsibility segregation as a service. So going back, I'll give you the links to these projects, but what I did was I implemented this shopping cart, and I did two forms of it. I did a key value version of a shopping cart, and I did an event source version of the shopping cart. And all the source code is in a couple of Git repos I'll give you the links to in a minute. And I just wanted to show as kind of an example of using, I call it event sourcing as a service and key value as a service. they both of these two services, they're functionally equivalent and they're completely independent of each other. They're just examples, but they both share a very similar API. Add item, remove item, change item, check out the cart, delete the cart, those types of things. So that's one thing I implemented. The view is another component. So in Akka Serverless, you create a service, and that service is composed of service components. So service components are things like an event sourcing as a service, a CQRS queryable view as a service. So these components make up a service. So all the APIs of each of these individual components contribute to the total API of the deployable service. So the service is also I was always looking for the unit of deployment. I have my project. So there's a shopping cart service project. Typical normal Java Maven project, and then there's a shopping cart. I've got another one I call shopping cart pub service. So another thing that I did to show as an example is that I added it's a kind of a topic subscriber as a service. So there's an implementation where I can consume messages from a topic, and if necessary, and this demo is quite simple, so there's just a small change or a small bit of data transformation that occurs, but there's another component that takes in messages from a topic and then forwards them to the event source as a service, the shopping cart service. And there's one for the event source version of the shopping cart service, and then there's another example doing the same thing, a different topic, consuming those topic messages and forwarding them into a key value as a service. So to produce those messages, I created a separate small little project that has a kind of the RESTful gRPC front-end API, so I can curl or gRPC curl commands to this guy, and this service will write those messages into a topic, just as a demonstration. But also what I was trying to show is you build services with these service components, and these service components are these different types of functions as a service type of thing. So this is, I think, one of the key features of Akka Serverless. Is that you can build all these different components. You can build key value as a service, databaselessly, function as a service, very fast. You're focused really primarily on the business logic and not much of anything else. That's the big promise of serverless. Event sourcing as a service as well. And then, of course, especially with event sourcing, it's CQRS almost always goes with it. Command query responsibility segregation, the separation of creating events versus making those events queryable. There's the write side and the read side. The right side is the event sourcing side. The read side is CQRS. With key value, the right side is a state store. The read side is queryable views. So you implement these things quite simply, but also consuming from topics and talking to external services, things like that. So here's the two sample projects. It's under my user in GitHub, McKee H3, and if you just look for shopping cart Java Akka Serverless or shopping cart pub Java Akka Serverless, that's the source code of what I was just showing you. You could take this, deploy it to Akka Serverless using a free trial or free account, and give it a try. Now, the other thing I mentioned in the abstract for this talk was no cold starts. And actually, I want to go back a little bit because again, for the sake of time, I was wanting to, let me go back. right here. It flashed up and I didn't really cover it, but I'm calling this kind of a mini cold start, meaning that whenever we're retrieving the state from the database, I call it cold state. This just my terminology, but the way I look at state in a database is frozen. You don't change it there. You change it on the compute side. So on that side, the state is hot. But there's this kind of mini cold start that's occurring. So in a stateful system, as I showed you earlier, the idea is that we're not doing a cold start every single time we need to change the state once the state has warmed up and is in memory. And that's a big feature of the system. But back here, a bigger cold start, what I just showed you is kind of very fine-grained cold start at the entity level, at each shopping cart, those types of things. A bigger cold start feature, often you'll hear with serverless is they hate the cold starts. Well, with Akka Serverless, we don't have cold starts. And the reason being is that the way things work is that when we have to scale up, there's new instances of the backend system, that where things are running are started up and they're brought to life, but all this is happening before any work is moved over to it. And if I have this is actually a screenshot of a kind of a visual that of this happening where I can show scaling up and scaling down and how all this works. But basically, there is no cold start in Akka Serverless. And the reason being, again, is that we warm things up first. We're spinning up a JVM. That JVM starts up, it's running, it's ready to go. And then once that guy's up and running, then we start moving work over to it. This is Akka. We've been doing this kind of thing before serverless for almost a decade. And now we're applying this kind of technology to Akka Serverless. So there you have it. I think I finished almost on time. Thank you very much. I really would love to see some of you guys take a look at Akka Serverless. We're very excited about it, and we're working very hard to make it a great developer experience and a really interesting and kind of unique serverless implementation. You can check it out at lightbend.com at Akka Serverless. Thanks again.
Thank you, Hugh. Amazing presentation, and thank you for the code that will be looked into. I do have a question in the Q&A from Emmanuel. The idea is that you have only one instance of the writer. Otherwise, how do you handle concurrent updates? Or you always use data which is not susceptible to concurrent updates?
No, really good question. And it's the idea is that there is that single writer and there can't be concurrent updates. It's a natural way the system works. So that all the change requests for a given thing, and this is like a row in a database type of thing. It's a just like changing my shopping cart or changing your shopping cart. Those are two separate things. Each one of those things is handling incoming requests one at a time by design. So there is no concern for concurrency. That it's kind of a natural form of locking. And this is really the actor model, right? Actor model behavior actually is what's going on there.
Yeah, thank you for the answer. We don't have any other. Oh, Emmanuel has asked more questions. How is the view updated for your function that gets the carts by customer ID?
How is the view updated?
Yeah.
Yeah. So there's a separate process that is, as changes are being made, say into the state store, with key value or event sourcing, events are being added to the journal. There's a separate process that is picking those up as quickly as possible, and they're being persisted in the queryable store. So there is that, and this is a natural feature of CQRS is that there's a latency between the time changes occur to the data, like writing an event versus having that event be queryable. And that's what's happening in the background. The nice thing for us as developers is that we're only writing the code to create the events, and we're only writing the code maybe to manipulate the data as it's going into the view. But we're not writing the code that actually handles passing the data as quickly as possible. All that's being handled internally by the system.
Thank you. Let me check. Oh, no more questions there.